Hello from Anne at morganmaths.com. Today's video is to help you handle double-decker fractions, so fractions within fractions. Something that comes up quite a lot at AS, but especially at A2. So my preferred way of handling such question is to look at the denominators that are within the embedded fractions. So here, for example, the problem is at the denominator where I have a fraction. The denominator here is this 7. So what I'm going to do is I'm going to cancel that denominator by multiplying the bottom, the denominator, by 7. Can I do that? Only if I do the same to the top. And what's the results of that? Well, at the denominator, add 6 over 7 times 7, well, those cancel. I am left with 6. And at the numerator, I have 2 plus x is being multiplied by 7. And you no longer have a double-decker fraction. It works the same way if your fraction within fraction has an algebraic denominator. So here again, we've got a fraction at the denominator. So the problem is with the denominator. I'm having a look at this denominator, and this fraction has got a denominator of x plus 1. So I'm going to multiply the bottom, the denominator, by x plus 1. Why? So that I'm going to cancel this double-decker fraction in a way. If I multiply the denominator by x plus 1, I'm going to multiply the numerator by x plus 1 as well. So the x plus 1's now cancel. What am I left with? Well, at the denominator, I'm left with 6. And at the numerator, we need to watch out and keep our brackets. We're going to have 2 plus x multiplied by x plus 1. And then depending on what you need to do now, you might expand the brackets, you might do whatever is needed. So what if, like here, you have a fraction within the denominator, but it's not just a fraction alone, like this 1 plus 6 over x plus 1. Well, the idea is going to be exactly the same. So have a look at the embedded fraction, this 6 over x plus 1. To get rid of this fraction, you're going to need to multiply by x plus 1. Now, you can't just multiply that fraction. You have to multiply the whole denominator in order to get rid of this embedded denominator, if you want. So if you do this, you have to do the same at the top. Now, what happens if you do that? Well, if you do that, you end up doing, at the top, you're going to have 2 plus x multiplied by this x plus 1. And at the denominator, you're going to have the 1 that you multiply by x plus 1, plus this fraction of 6 over x plus 1 that you multiply by x plus 1. So these two x plus 1's cancel, and you're left with, at the numerator, 2 plus x over x plus 1, and at the denominator, 1 times x plus 1, so that gives you an x plus 1 plus 6, which you tidy up as an x plus 7, and the numerator stays as 2 plus x times x plus 1. So watch out when you do this. The approach is the same. You need to get rid of that embedded denominator, so you're going to multiply the denominator by x plus 1. But if you do that, you have to multiply every term at the denominator. Final example here, number 4. This time you've got two embedded fractions, so it's a triple-decker fraction if you want. So what are we going to do? Same approach. Have a look at the denominators within these embedded fractions, and the good news is that they are the same. So if you multiply the denominator by x plus 1, it's going to cancel the denominator at the numerator, at the denominator. And if you do the same at the top, then you're also going to be able to cancel it at the top. So if I show the steps, what happens then? You've got your 2 that's multiplied by x plus 1, and then you've got this 1 over x plus 1 that's multiplied by x plus 1. And what happens at the denominator, again showing all the step, 1 times x plus 1 plus the fraction that I had, this 6 over x plus 1, is multiplied by x plus 1. Let's check what cancels. Well, at the numerator, the fraction is simplified, and at the denominator, the same approach happens. So you can now expand your brackets, so we get 2x plus 2 plus the 1 left from the fraction, and at the denominator, same approach, x plus 1 plus the 6, because the denominator is cancelled with the x plus 1. And finally, you simplify, so you're going to have 2x plus 3 over x plus 7. And that's a nice, easy way to simplify these sorts of embedded fractions. Does it work when you're working with thirds? Absolutely. So the question on the left-hand side is actually an GCSE question, but it could happen at A level if it was a sure that, because otherwise you just type it in your calculator. So you're going to have the same approach here. Observe this mess of fractions within fraction. Look at the embedded fraction. The denominator is root 2, so you need to multiply the denominator by root 2. And you're going to do the same at the numerator. So now your fraction becomes 1 times root 2 is root 2. And at the denominator, I'm going to start doing it a little bit faster. So we have to imagine that we're going to do 1 times root 2. So here is going to give me a root 2 plus 1 over root 2 times root 2. We're going to cancel the denominator with this root 2 you multiply with. So you have a 1. Would I be finished here? Well, in terms of getting rid of these double-decker fractions, yes. Generally, you will then be asked to rationalize, which means you're going to multiply the denominator by its conjugate, so root 2 minus 1. Whatever you do to the bottom, you do the same to the top, and you're left with root 2 times root 2 to 2, plus 1 times minus 1 is minus 1, and at the top, root 2 times root 2 is 2, minus root 2, final simplification, 2 minus root 2 over 1, 2 minus root 2. Does it work with the second example? Of course it does. Same approach. Look at the denominator within these embedded fraction. Oh, we were lucky here because they are the same. So what I'm going to do is I'm going to multiply the top and the bottom by 2 root 3. Top and the bottom by 2 plus root 3. Now you might be wondering, why am I not multiplying by 2 minus root 3? Well, I prefer to do one thing at a time. At the moment I'm not rationalizing. I'm resolving this issue, this messy situation of fractions within fractions. So if I do that, what am I left with? Well, I'm going to have 1 times this 2 plus root 3 plus the fraction. We are going to cancel down the denominator and this 2 plus root 3, so I'm going to have a plus 1. And at the denominator, similar situation. 2 times 2 plus root 3, and then minus 3, as the fraction cancels the denominator, cancelled by this 2 plus root 3. Next stage, let's tidy up. So we now have a 2 plus root 3 minus 1 over 8 plus 4 root 3, I'm expanding my brackets, minus 3. So this gives us, oops, it's not a 2, it's a 1 plus root 3. So that's a 1 plus root 3 over 8 plus 4 root 3. And at that stage, we are now ready to rationalize. So the next step would be to rationalize. The next examples I'm going to look at, they look the same, but they just have one small twist. And the small twist is within your embedded fractions, the denominators are not the same. So what are we going to do here? We're going to look at them one by one. At the numerator, if we want to get rid of this embedded denominator, we're going to need to multiply it by x plus 1, which means we have to do the same at the denominator. So that will sort out the first embedded denominator. To sort out the problem at the denominator with this embedded fraction with denominator of 2x plus 1, this time I'm going to need to multiply it by 2x plus 1, which means I have to do the same at the numerator of 2x plus 1. And here for this first example, I'm going to write all the steps. So what happens then? So we had a 2 that's going to be multiplied by x plus 1 and by 2x plus 1. We had this fraction which has to be multiplied by, let's study x, x plus 1, but also 2x plus 1. And at the denominator we had a 1 that we're going to multiply by x plus 1 and 2x plus 1. And we also have this 6 over 2x plus 1 that's going to be multiplied by x plus 1 and 2x plus 1. Let's have a look. What cancels here? Well, the denominator within the numerator is going to be cancelled. The denominator within the denominator is also going to be cancelled. And we're going to have an awful lot of brackets to open. So we are going to then have this 2 times x plus 1, so doing it in 2 steps. 2x plus 2 multiplied by 2x plus 1, and then we're going to multiply that by 1 times 2x plus 1. I don't have to write the 1, but I want to show all the steps for you here. And at the denominator we're going to have this x plus 1 times 2x plus 1, so x plus 1 times 2x plus 1, and we're going to be left with 6 times x plus 1. The next step will be to expand all of these brackets very carefully. So we're going to have 4x squared plus 4x plus 2x, so that's going to give us plus 6x, and then 2 times 1 plus 2, and we're going to add the expanded second bracket of 2x plus 1. At the denominator, we're going to have a 2x squared, and we're going to have 2x plus 1 more x, so that's going to be plus 3x plus 1, and then we're going to add to that 6x plus 6. And your final stage will be to collect like terms. So at the top we have 4x squared plus 6x plus 2x, so that's a plus 8x plus 3. And at the denominator we have a 2x squared plus 9x plus 7. What about the second example here? Well, it's the similar idea. This time we don't have two different denominators. We have all of them are just different denominators. So what you ought to do, you could multiply by every denominator here and you're going to have something very complicated. Or you can do a little bit of observation and say, right, what's going to cancel with that? The highest denominator is 12x. Well, 12x is a multiple of 2x. It's a multiple of 6. It's a multiple of 4. It's a multiple of 3x. So actually, by multiplying the top and the bottom by 12x, we're going to be able to simplify everything in one step. So let's have a look. I'm going to do it in steps so you can see how I simplify. So we have a quarter multiplied by 12x. We're going to have plus 2 over 3x multiplied by 12x. And at the denominator we have 1 over 6 multiplied by 12x, and then we're going to have minus 3 over 2x multiplied by 12x, and then finally we're going to have 5 over 12x multiplied by 12x. Okay, we now need to simplify each of these fractions. Let's do them one by one. So 12x times a quarter, well, the 4 and the 12 cancels, we've left with 3x. And then 2 over 3x times 12x, the x cancels. And then the 12 over 3 means that you're left with a 4. Add the denominator, the 1/6 with the 12, that cancels, you're left with a 2x. And then minus 3 over 2x, we can cancel the x, and we can cancel the 2 with the 12, we're left with 6. and with your final simplification, the 12x is going to cancel down with the 12x. You're just left with the 5. What is left now in this fraction? So at the numerator, we're going to have 1 times 3x, so we're left with 3x, plus 2 times 4, plus 8. At the denominator, 1 times 2x, so we have a 2x, minus 3 times 6, minus 18, plus 5. We are almost done. Final simplification, 3x plus 8 over 2x minus 13. Now you can skip some of these steps. If you feel you don't need the second step, of course that's fine. You can go to the next one. But take your time, because there's a lot to be lost here. So just watch out. One place where these double-decker fractions come up a lot is when you are trying to simplify some trig identity. So let's have a look at this one. First one is more AS, the second one is more A2. So if you need to simplify this, you're going to need, generally, we're going to get the tan x expanded out, written as sin x over cos x. So I'm going to start by splitting all these tan x, because I've got in the same equation, the same expression, sine, cos and tan. So to simplify, let's see if we can cancel anything out. And then we've got a sin x. So I've really displayed here all of the tan x. Now, we've got lots of double-decker fractions. However, at least we have the same denominator within each of those. We've got some cos x all over the place. So what we're going to do then is we're going to multiply the top by cos x and the denominator by cos x. What's left at the numerator? Well, cos x times cos x is 1. Sin x times cos x over cos x, the cos x will simplify. We are going to get plus sin x. And finally, minus, we have cos x multiplied by cos x, so it's cos squared x. If we do the same at the denominator, then the two cos x are going to cancel. You're left with sine squared x. Okay, what could we do next with that? So generally they will tell you what the target is. On here, I think I would spot that there's a 1 and a minus cos squared x, and that's equals to sine squared x. So we end up having sin x plus sine squared x over sine squared x. And if we factorize 1 over sine x at the numerator, we're left with 1 plus sine x at the numerator, sine squared x at the denominator. We simplify and we get 1 plus sine x over sine x. So example number 2 with the A2 question where we have sec, and here in the same expression we've got sec, we've got cos, we've got cosec, and we've got some sines. So let's expand all of those to display the fractions and just get everything in terms of sine and cos. So we're going to have 1 over cos x minus cos x, and the denominator is 1 over sine x minus sine x. If you are just in year 12, if you haven't looked at the year 13 contents, then you won't be familiar with sec and cosec. This appears in the year 2 of the course. Right, what are we going to do? Well, at the top we need to multiply by cos x, so we need to multiply the top and the bottom by cos x. At the denominator we need to multiply by sine x, so we're going to do the same at the numerator. We're going to multiply by sine x. And then what happens? Well, if we look at them one by one, cos x, sin x divided by cos x, the cos x is going to cancel. So we're going to be left with, so we're going to cancel the cos x, we're going to be left with sin x. And then on the second term is a minus, we're going to cos x multiplied by cos x sin x, and that's going to give us cos squared x sin x. What about the numerator? So the numerator, another way to think about it, is we're going to multiply the fraction by cos x sin x, and we're going to multiply the second term by cos x sin x. So in terms of a fraction, the sin x will cancel, we're going to be left with cos x. and then what do we have for the second part? We're going to have sine squared x cos x. Right, what could we do next? Not obvious, but we've got some sine everywhere at the top, we've got some cos everywhere at the denominator, so we could do a little bit of factorizing. So we're going to have sine x, and then we'll be left with 1 minus cos squared x, which I recognize straight away as sine squared x, by the way. At the denominator, we're going to factorize cos x, and that's going to give us 1 minus sine squared x, which I recognize as cos squared x. So let's tidy up. We now have sine x multiplied by sine squared x over cos x multiplied by cos squared x. Well, this really is sine cubed x over cos cubed x, and this means that we have tan cubed x.